We are covering biochemical oxygen demand, chemical oxygen demand, and the dissolved oxygen sag curve as modeled by the Streeter-Phelps equation for the FE Civil exam. You will find these topics in the Environmental Engineering section of your NCEES FE Reference Handbook. First, let's distinguish between BOD and COD. Biochemical oxygen demand, or BOD, is the amount of oxygen that microorganisms consume to decompose organic waste. The standard test, BOD5, measures this consumption over 5 days at 20 degrees Celsius. Chemical oxygen demand, or COD, is a much faster test that uses a strong chemical oxidant to break down both biodegradable and non-biodegradable organic matter. For the exam, remember that the COD value will always be greater than or equal to the BOD value because it accounts for more types of waste. When wastewater with a high BOD is discharged into a river, the bacteria start consuming the waste and, in the process, use up the dissolved oxygen, or DO, in the water. This is where the DO sag curve comes in. The curve shows how the DO level drops downstream from the discharge point and then slowly recovers as the river is reaerated from the atmosphere. The lowest point on this curve, the critical point, represents the worst-case scenario for aquatic life. This entire process is modeled by the Streeter-Phelps equation. The equation is a balance between two competing processes, deoxygenation from BOD exertion and reaeration from the atmosphere. The deoxygenation rate is represented by the constant Kd and the reaeration rate by Kr. Both are typically given in units of per day. A common exam problem involves finding the time it takes to reach the minimum DO, known as the critical time, or TC, and the corresponding oxygen deficit, called the critical deficit. The formula for critical time is provided in the handbook. A critical trap on the exam is correctly calculating the initial oxygen deficit, D0. This is not the initial DO value itself, but the difference between the saturated dissolved oxygen, DO-sat, and the initial dissolved oxygen, DO initial, right after the wastewater and river have mixed. For example, if a river saturated at 9.1 milligrams per liter of DO mixes with effluent, and the resulting initial DO is 7.5 milligrams per liter, your initial deficit, D0, is 9.1 minus 7.5, which is 1.6 milligrams per liter. Another trap is unit consistency. The rate constants Kd and Kr must be in base E and have units of inverse days for the equations in the handbook. If you're given a rate constant in base 10, typically denoted with a capital K, you must convert it. Also, be sure that the ultimate BOD, L0, is the value immediately after mixing, which often requires a simple mass balance calculation of the upstream river flow and the wastewater discharge. To remember the rate constants, use this phrase. Kd is for the death or decay of oxygen due to waste, while Kr is for the river's recovery or reaeration. For free practice questions, AI-powered explanations, and more exam prep tools, visit openexamprep.com. That's openexamprep, all one word, .com.